Perhaps the simplest way to describe a plane, W in R3, would be to use a Cartesian equation. So we can have W, which is the collection of points in R3. So this is the form. There are points in R3 that satisfy the condition that in order to be on the plane, you need to have AX plus BY plus CZ equal to D, where A, B, C, and D would be given. They'd be specific numbers for the purpose of whatever exercise you're working on, and X, Y, and Z would be the coordinates of the point of interest in R3. The vector ABC, which consists of the three coordinates here, we call that the normal vector to the plane. And D is equal to, D is some constant, some scalar number. You can write this using the notation we saw in the previous section, n times x equals d, where here d would be not a direction vector, it'd be a scalar, x is the vector xyz here, and n is the vector abc. I can use the inner product to describe the plane in Cartesian coordinates. That's called the point normal form, and you can sort of see it here. I specifically added in the d so that whatever we have on the right hand side is a 0, right? Remember what we had was n times x is equal to d. Well, this is sort of the same rewriting of this, but because we have a v0 here, we can actually write d as n times v0, and then take the nv0, put it over here. In my specific notation, instead of calling it the vector x, I just call it the vector v here, so it would be this thing. And this is what we're seeing. We have n times v minus v0 will be the scalar 0, not the vector 0, right? Because this is an inner product of vectors. So it's just another way to describe a plane. So if you had to give the Cartesian equation of the plane W that goes through the vector 1, 0, 3, so that's one point on the plane, and for which the normal vector is minus 1, 1, 2, then you're looking at this, right? Here's the plane W, here's a point, the point 1, 0, 3, say, and you have a vector that is perpendicular here, and this is the vector n, which is minus 1, 1, 2. That's the plane in question. Well, what's the equation according to the point normal form? You can write W as the set of all vectors in R3 for which V minus V0 dot product with n is 0. Here V0 is given, n is given, V is not given. These are the variables. So it varies in the description. So okay, let's spell it out. V is a vector in R3, so it looks like x, y, z. And so we have it here again, x, y, z. It shows up in two locations. Minus V0, which is the point which is right here. Sorry. Dot product with the normal vector minus 1, 2. So if I just write it out and I distribute these things, I do the computations, I'll have the vector x minus 1, y, and z minus 3 inner product with minus 1, 1, 2, and then I just multiply each of the components pairwise and do the sum. And that gives me minus 1 times x minus 1 plus 1 times y minus 0 plus 2 times z minus 3. And that should be equal to 0. That's the point normal form. I can just clean this up, leave all the x, y, z's on one side, everything else on the other side, and I get the Cartesian equation. The plane W is the set of all x, y, z's where minus x plus y plus 2z is equal to 5. So that's, I mean, in the second case, in this form here, it is easy to tell when a point is on the plane. Let's say I want to know, is the point 0, 0, 0 on the plane? Let me replace x by 0, y by 0, and z by 0 in the Cartesian equation for it. I'll have minus 0 plus twice 0. That's 0. 0 is not equal to 5. 5 is not in W. So it's easy to tell when a point is on the line, on the plane, but it's not necessarily easy to find a point. I mean, it's not difficult to find a point, but it's much easier to find a point by using the this expression here, right? Or is it that much easier? Perhaps. Well, we know V0 is on the plane because V0 is by construction a point on the plane. So if the idea is to find any point on the plane using the point normal form is great because you have a V0. If the goal is to determine if a point is on the plane or not, it might be easier to actually use the Cartesian form. But they're really the same form, right? If you actually think about it, it's just that one of them has been explicitly written out. Here's your normal vector, minus 1, 1, and 2. So even though they look different, and even though a specific form might more naturally avail itself in your mind when you try to do something, they're literally the same thing. They're really not that different. What if you were trying to find the distance from a point to the plane? Well, you need to know the actual point itself, its coordinates. Here we have 1, 2, 3, but it could be anything else. And we have a specific plane, the plane that has Cartesian equation 3x minus 4z equals minus 1. You notice there that there's no y coordinate in the equation of the plane. That's okay. That's an acceptable thing. If what's missing is a y or an x, you'll be reminded that you're talking about something in R3 because there'll be a z. But if what was missing was the z, you might forget that you're working in R3 because you'll see an x and a y and you'll think you're in R2. Just remember from the context, because the point P has 3 coordinates, we had to be in R3. How do we do this? How do we find the distance from a point to the plane? Well, the distance from a point to the plane, there's like a lot of possible distances, right? If this is the plane W and my point P is here, like here's a point and here's a distance. Is this the distance that I mean? Well, because there'd be infinitely many distances if that was the case, and that's not good. Typically, when we ask a question like this, there is a unique distance that is of interest to us. In this case, it's the distance which is the smallest. So we're looking for the point Q in the plane that is going to give us a vector here, which is perpendicular to the plane through P. And we know how to do this, right? This is a projection. At least the projection of A minus B. How it works is this. You pick any point on the plane. I picked 1, 0, 1. Is it actually on the plane? Let's verify. 3 times 1 minus 4 times 1 is 3 minus 4 is minus 1. So yeah, the point A here in question is indeed on the plane. But you could find any other point in the plane and that would work just as well. And Q is the point that is of interest to you. You want to find the point which is the closest point on the plane to the point P that is given in the problem. So what you're really interested in for the distance is the length of the projection of the vector A minus P. Because A minus P would be here. This is the projection, this is the projection against the normal. Projection against the normal here. And then you're looking for the length of this quantity. So where are you projecting? You're projecting the vector A minus P. Let me draw it again here. This is A minus P against or along the normal vector. And that distance here will be the distance of interest to you. So you compute it. What's the length of the projection? It's the norm of the difference, the norm of the projection of the vector P minus A along N. P minus A, you can compute it, right? P is the vector 1, 2, 3. A is the vector 1, 0, 1. If you subtract 1, 2, 3 from 1, 0, 1, you will get 0, 2, 2. So that's the thing you project along or against the normal vector, which we know it's given. It's literally in the Cartesian coordinates, 3, 0, minus 4. So the answer for whatever's inside the norm is going to be a multiple of the vector 3, 0, minus 4. And we use the formula. This is a formula that you have to remember. It's not that complicated. You do the inner product of the quantity or the vector that we're trying to project with the vector on which we project. We divide that by the length of the vector on which we project, and we multiply that by the actual vector itself on which we project. So the dot product 3, 0, minus 4 with 0, 2, 2 would be 3 times 0, which is 0, 0 times 2, which is 0, and minus 4 times 2 is minus 8. We add all of these things together, we get minus 8. The length of the vector 3, 0, minus 4 will be the square of 3 plus the square of 0 plus the square of minus 4. And you take the square root of that. But we're looking really at the square of the length, not just the length, even though I've said the length. The formula here says that this is going to be the square of the length, and that gives us 25, and then we have the vector 3, 0, minus 4. So we have 8 over 25. That's a scalar. We can take it out of the length. It won't affect this, and we just measure the length of 3, 0, minus 4, which we've already done here, right? I mean, it's the square root of 25. So we end up with 8 times 5 divided by 25. You can compute that fully, but you can also write 8 times 5 divided by 5 times 5. And this is always going to sort of play nicely because of the formula that we're using right here, right? These are the same sort of quantities. And so you can cancel out a 5 in the numerator and a 5 in the denominator, and you get 8 over 5. So the point in question, the point that is the closest, well, we haven't really computed it. We haven't explicitly computed it, right? It would be this thing here, 8/25 of 3, 0, minus 4, but we're not asking for where the point is located. We're asking for the length. Is what I said true here? Is it really the point that's the closest? Well, no, because what we've computed was always the projection of p minus a over the vector n. So you have to be careful here not to confuse the question that's being asked. You're asked to find the distance from the point to the plane. You know that in theory you need to find this vector q. That would be the closest point, and then you could look at the difference between p and q. But the way we've computed this, we haven't explicitly found the point q. We just found the length of the projection on the normal. Don't get confused by that. How would you find then the intersection of two planes, x plus y plus z equals 3 and x minus y minus z equals 2? So for this, you need to find all of the points in R3 that satisfy both equations. There's many things you can do to get there. Here's one way in which you could do it. You could subtract the second equation from the first, right? If both of these equations are true, if you subtract one from the other one, you'll get something which is still true. So what does that mean? Well, I'm going to, x minus x is 0, y minus minus y, that's 2y, z minus minus z, that's 2z, and 3 minus 2 is 1. All right, so I showed you how to subtract one equation from the next. I just told you how to do it, but we haven't really defined what it means to subtract an equation from another. Sure, upon being told what it is, you're like, yeah, that makes sense. I can just subtract the x's, the y's, the z's, and constant terms. But why is that actually what we need to do? When we talk about linear systems in general, we will describe a procedure that allows us to sort of find these intersections, find these solutions without really having to worry about things like subtracting equations from one another. So we end up with 2y plus 2z equals 1. So that's also something that's true. It's something that comes from both of these equations. We can then solve for y. I just send the 2z to the other side. 1 minus 2z, divide by 2. So y is going to be 1 over 2 minus z. Okay, that's good. What do we do with this? Well, from the first equation, in that case, what happens? The first equation tells us that x would be equal to 3 minus y minus z. And we said that y has to be equal to 1 over 2 minus z. So that gives me x is equal to 3 minus y, which is 1 over 2 minus z. Great. And that's equal to 5 over 2. Why? Well, 3 minus 1 over 2, that would be 6 over 2 minus 1 over 2, 5 over 2. And I have minus minus z, which is z minus z, which is 0. There's no more z. So x has to be equal to 5 over 2. Z, there's no restriction on z. Z could take on any value here. So we're going to call it t. T is some real number. Now we have a specific value of x. It's equal to 5 over 2. Z can be anything. Y, well, y can not be anything without taking into account what z is, because the way we set it up here, we have that y is equal to 1 over 2 minus z, 1/2 minus z. So 1/2 minus t, because we said that z is equal to t. And what we have is a vector parametric form, or a parametric form for the line. The value of x is always 5 over 2. The value of y, 1 over 2 minus something. Value of z would be 0 plus t equal to, well, there's no t's in x. There's minus 1t in the y, and there's 1t in here. And here's the vector parametric equation. V0, which is 5 over 2, 1 over 2, 0, plus t, the direction vector, 0, minus 1, 1. If you wanted to rescale the direction vector, you could, but you cannot rescale the point that's on the line, because it's not a vector here, it's a point. These are different things. Well, can we do something analogous to what we did for the geometry of lines? What's the geometry of planes? We can compute the angle between two lanes. We know how to do so if we use the inner product, right? We know that the inner product of two vectors gives us an expression that, amongst other things, contains the cosine of the angle between them. You write it out here. The inner product, u with v, gives us a scalar, which is the norm of u times the norm of v times the cosine of the angle between the two lines. How do we measure the angle between two planes? Well, we know how to work with lines, so we know how to work with vectors. With planes, it's a little bit more complicated, right? It's even harder to envision them. Well, thankfully, when we have a plane, we have a unique vector associated with it, the normal. The normal vector is that one vector that is basically perpendicular to the plane. So the angle between two planes would be the angle between the normal vectors of the respective planes. That's something we know how to compute. If you look at R, there's no plane in R. R is just a line. In R2, there's only one plane, all of R2 itself. And that's analogous to saying that in R, there's only one line, all of R itself. If you have two distinct planes in R3, either they're parallel, and by that we mean that the angle between their normals is either 0 or pi, or they intersect in a line. That's analogous to saying that if you have two distinct lines in R2, either they're parallel or they intersect in a point. Is it possible that if you had two distinct planes in R4 then, to maintain the analogy, either they would be parallel or they would intersect or they would be skew planes? Well, the problem, this question is difficult to answer because we don't really have a way to describe a plane in R4. I know how to describe one in R2. That's the whole plane. I know how to describe one in R3. I can use the point normal form or the Cartesian form. But I don't actually have a way to describe a plane in R4. You can sort of look at the sort of a pattern that emerges, right? Let's say you have a parametric equation in one variable. In Rn, that's always going to give you a line, no matter what the n is. An equation of the form ax equals b in one space, which is R, gives us a point. An equation of the form ax plus by equals c in two space gives us a line. An equation of the form ax plus by plus cz equals d in three space gives us a plane. And an equation of the form ax1 plus bx2 plus cx3 plus dx4 equal to e in four space gives us I don't know what. I don't actually have a way to envision this. The Cartesian form is also known or called the normal equation. And what it does is it removes one dimension from n. So the resulting geometric object is an object of dimension n minus 1. Right? A point is an object of dimension 0. If I describe an object using a normal equation here in one space, I'm going to get a 0-dimensional object. Line is a one-dimensional object, Cartesian form, normal form, in two space, so I get n minus 1, or 2 minus 1. Basically, the result of this normal equation, ax1 plus bx2 plus cx3 plus dx4 is equal to e, in four-dimensional space would be a three-dimensional object. It's not just a plane, right? It's something that is akin to three space living inside of four space. What we could say, based on the analogy, is that if you have two distinct hyperplanes, this is the name we give to these things, in R4, so objects of dimension 3 in R4, then either they're parallel or they intersect in a plane.